As a paleontologist, I often get asked this particular question a lot during interviews with non-scientists or with journalists. What is it all good for? It's hard to answer. For example, would you ask an artist, what is it all good for? Or a football player who's just won the game, what is it all good for? Well, we're apt to reply, well, it's entertaining, or it makes life more fun, more enjoyable. But I think what they're really asking is, how does this generate money? So a journalist or a member of the public would be impressed when the artist would say, I sold this latest work of art for $20,000. Or the football player that makes $3 million a year. But what does a paleontologist or any scientist say about knowledge? What value does knowledge have? Today, knowledge is cheap. A quick search on Google or reading through a Wikipedia article online will quickly fill you in with the latest information. And it just costs you, well, an internet connection. Information has become abundant, and hence the value it provides appears to be much smaller than ever before. Think about what knowledge required before the internet, when you had to go to the library or buy a book or purchase a newspaper at a newsstand or take a class. Knowledge was rare and hence seen in society as valuable. But what about new knowledge? What value does that have? In science, often what the public is asking is, will this new knowledge save the life of someone? Does this new knowledge benefit me or my fellow humans? Then it's often deemed as valuable. So in other words, will the study of paleontology, the study of fossils, my own discipline, will it save the world? Well, in this video, I'm going to tell you the story of one of the most famous fossils that you've never heard of, but which just may save the world with the information that it contains. This is the fossil. Well, one very similar to it. It's a Blimanite. Blimanites are an extinct group of squid-like animals that lived during the age of the dinosaurs. They're common fossils because they have an internal skeleton which is composed of what's called a rostrum. This is a bullet-shaped fossil, which has a hollow center that you can see there. And this helped keep the animal afloat as it swam around in the Jurassic oceans. Now, this rostrum is composed of a mineral, and that mineral is called calcite. Now, calcite is calcium bonded to carbon and 3 oxygen atoms. Now, you're probably wondering, how would a fossil Blimanite save the world? Well, we need to go back to October 30th, 1961, when this happened. This is the Tsar bomb, the largest and most powerful nuclear weapon ever detonated. Anything within a 60-mile range was totally destroyed. 170 miles away, heat waves blasted and set fires, and 430 miles away, shock waves broke windows, and seismic waves bounced within the interior of the Earth, down to the outer and inner core boundary. What technology brought about such a bomb? Well, this bomb imploded a new substance, isotopes of hydrogen, a cocktail of deuterium and tritium, which are encased within the bomb. These H-bombs, or thermonuclear weapons, employ not only fission, the breaking apart of atoms to produce energy, but also fusion. The blast was powerful enough that it also set about causing this fusion, the same process that generates the sun's energy. Fusion is the bringing of neutrons and protons together to form new elements. In this case, the fuel for this fusion is deuterium and tritium, a stable and unstable or radioactive form of hydrogen. Now, where do you find this deuterium and tritium? Can you mine it? I mean, where does it come from? Well, this is Harold Urey, who won the Nobel Prize in 1931 for discovering deuterium. And he found it in a glass of water. Inside each glass of water is a sea of water molecules. They're composed of oxygen and hydrogen, with 2 hydrogen atoms bonded to each oxygen atom. Now, some of these hydrogen atoms have just a single proton, while just a few of them have both a proton and a neutron. Scientists had measured the mass of hydrogen, and they observed that it is 1.00794 atomic units of mass. Now, if there's only one type of hydrogen with just a single proton, then the atomic mass would be 1.0000000. It'd just be even 1, just 1. This little bit of remaining, the 0.00794, means that there are a few atoms with a mass of 2, having both a proton and a neutron. But it's not very many hydrogen atoms that are like this. Now, to isolate atoms that have both protons, a proton and a neutron, Harold Urey and others, well, they begin boiling the water. As the boiling temperature of water molecules with the unusual atoms of hydrogen have a slightly higher boiling temperature, around 105 degrees Celsius. By boiling off the hydrogen with just a single proton at 100 degrees Celsius, the tiny little bit of remaining water at the bottom of the beaker would be enriched in the weird hydrogen with both a proton and a neutron. Now, this process required a huge amount of water, as just a tiny, tiny little drop of heavy water was present through each distilled process. The mass of the resulting water was then run through a mass spectrometer, and the number of hydrogen atoms with a mass of 2, they increased. The mass became closer and closer to 2 with each process from the beginning point of 1.00794, the starting point. We call this enriched water, in that it has more of those weird hydrogens, or heavy water because it contains more atomic mass than regular water. Now, Harold Urey discovered this new enriched water. He proved that it existed, and he won the Nobel Prize in 1931, calling the isotope of hydrogen deuterium. Isotopes are atoms which have the same number of protons but different numbers of neutrons. Isotopes can be both stable or radioactive. Most isotopes are actually radioactive in that the nucleus of the atom can't handle the addition of neutrons, and it falls apart rather quickly. However, some radioactive isotopes can kind of stick around for much longer. The radioactive isotope of hydrogen with 2 neutrons is tritium, which decays with a half-life of about 12 years, which means that after 12 years, half of it will have decayed to helium. Now, in fact, a mixture of tritium and deuterium with intense energy can form helium through the process of fusion. This fusion is what in part makes the sun glow so bright. Thermonuclear fusion. This was the secret fuel of the H-bomb. Now, Harold Urey realized in the years that followed World War II that these new super bombs were a major threat to the Earth, and strongly advocated for a world government agency to prevent their use. But back in the lab, Harold Urey was interested whether the process he used to enrich the water could work with other stable isotopes. And he wondered about using his knowledge to understand the history of our planet. Carbon, like hydrogen, also has a stable isotope. Most carbon is 12, meaning it has both 6 protons and 6 neutrons. However, there's a small amount of carbon with 13, with an extra neutron. So, how do you enrich carbon so that you can either have carbon with more carbon 13 or depleted with more carbon 12? Well, Harold needed a standard that he could compare with, and he reached for a fossil, the BD Blimanite, which, as you remember, has carbon inside of it in its crystal structure of calcite. It also has oxygen, which Harold was also interested in studying the stable isotopes. So Harold measured the atomic weight of the calcite in the BD Blimanite lying just in his lab. It was just something he just picked up. It was a fossil he thought was kind of cool. And he's like, I wonder what this has. And he found that it has an atomic weight of carbon around 12.011, which means that it is mostly carbon 12 with a small amount of carbon 13.011 to push it over the edge and be slightly more than that 12 even, which would be expected if the fossil was composed only of carbon 12. Now, he decided to set about measuring all sorts of things that contain carbon to see how they compared to the BD Blimanite. Now, as students and the whole community of geochemists began to use the acronym BPDB for the ratio of carbon 12 to carbon 13 as they compared to this standard. So, if the substance had more positive values, so on this side, then it relative to more positive values means it has more carbon 13 than 12 when compared to our fossil standard, the BD Blimanite. If the values were more negative, it meant that it had less carbon 13 relative to 12 when compared to our standard, the BD Blimanite. We can see on the scale that rocks tend to be over here, near where we have the BD Blimanite, which is our 0 standard here. So we have limestone rocks and marbles that are like 1 and 2. We have basalt, lava rocks around -2. Other fossils are going to be close here, like fossil ammonites, close relative, are going to be around -2, kind of within where the fossil is. Diamonds are going to be in like deep mantle rocks, can go down to like -5. So kind of right in this scale. But as we move down here, we get into where are called the organic sources of carbon. So things like corn, a lot of the foods we eat, sugar, graphite that you use in your pencils, and wood, -25, pretty low. Coal, also -25. Oil shell, even getting lower, -31. And down here we have like gilsonite, which is -40 to -60. And petroleum, which is between about -35 to -50. So these negative values mean that they tend to have more carbon 12 and hence are more negative when compared to our fossil standard, the BD Blimanite. The most negative sources, of course, are things like coal and petroleum. They're way down on this scale. This refined organic carbon molecules they make really great fuels, which we can burn in our machines. So what's causing all of these things down here to be more negative, to have much more 12 than 13? Well, part of it has to do with the fact that carbon-12 tends to preferentially like to bond to hydrogen rather than oxygen, and becomes depleted in carbon-13, for example, when plants use the carbon from the atmosphere to make sugars. And these sugars then are broken down in the earth, producing smaller chains of carbon and hydrogen. This process is called fractionation, which releases more of the carbon-13, and the source then becomes more depleted, making the atomic mass of the carbon closer and closer to 12. But where on this scale does the carbon dioxide that I just filled this balloon with sit? The air in the atmosphere. Well, it sits around -7 to -8 on this scale, right about here. But it's moving. Through the pioneering work of Charles Keeling, we've documented about a 25% increase in the amount of carbon dioxide in the atmosphere from 1958. And now, with the help of the standard, the BD Blima, we can measure the stable isotopes of the carbon in the atmosphere over time. If the increase of carbon dioxide is coming from the burning of fossil fuels, we should see the ratio values of carbon-13 become more and more diluted with the abundance of carbon-12. In other words, the values will become more negative over time. However, if the carbon dioxide is coming from volcanoes or the melting of rocks, then we would see it become more positive over time. This is how we can trace the source of the increase in carbon dioxide in the atmosphere. This graph here shows the depletion of carbon-13 in the atmosphere. The atmosphere over time is becoming enriched in carbon-12 from the burning of fossil fuels, such as this oil. Values have dropped from around -7.8 to around -8.4 in 2008. And this drop in the ratio indicates that fossil fuels over here are the source for the increase in carbon dioxide in the atmosphere that's leading toward global warming. In the fossil record, such decreases in the carbon isotopes are often seen during periods of mass extinction. And these negative excursions are the primary indicators that something bad is happening with life on the planet. Here is the negative excursion with the KT boundary, when the dinosaurs went extinct. In the far future, the sediment that currently is being deposited around the world will show a negative excursion in the isotopes of the carbon that's being laid down, a clear signal that we are living during a mass extinction.
I think that what is so fascinating, to me at least, is that just by understanding the chemistry of a long extinct fossil from the age of dinosaurs, we are able to understand one of the greatest threats to the survival of life on the planet. The study of paleontology provides all sorts of very valuable information that is priceless, especially when it comes to understanding how our planet works. I hope you continue to stay tuned. I'll be posting future videos on the topics of paleontology and geology this year, so be sure to subscribe, like this video, and share it with your friends. If you'd like to learn more about the power of stable isotopes, I highly recommend this wonderful textbook, Principles of Stable Isotope Geochemistry by Zachary Sharp.